Dear students, Assalamu alaikum. Today I am again with a new class for class 12th, and our today's topic is magnetism. So let me first tell you what is a magnet, what is its historical background, where it was found. As you might have read in class 10th about this magnet and about its historical background. It was a Greek philosopher, and his name was Thales. He was from Miletus. Uh, as you know that he was from Greece, so there is a place in Greece that is known as Miletus. And in 600 BC, 600 BC, which means that near about 2500 years ago, he found that a naturally occurring ore of iron. As you know that the ore of iron, it is Fe3O4. It attracts a small pieces of iron, steel, cobalt, nickel, etc. towards it. He had a city uh, made up of iron oxide. It was made up of iron, and it by chance attracted the pieces of these iron, steel, cobalt, nickel, etc. So this ore was found in the district of Magnesia in Asia Minor in Greece. There is a district in Miletus that is in Greece known as Magnesia. This Thales was from that district, and he found this ore in that district, and hence this ore was named, iron ore was named as magnetite. Now, what is magnetism? The phenomenon of attraction of small bits of iron, steel, etc. towards the ore iron is called magnetism. The iron ore showing the property of magnetism is called a natural magnet. So this natural magnet is naturally found in the from the earth. Then Chinese discovered that a piece of magnetite, now which we call now magnet, earlier it was called magnetite. When this magnet is suspended freely, it always aligns itself in the north-south direction. It always points in the north-south direction. If you rotate it towards east-west direction and let it free, it will again align itself in the north-south direction. It will never stay in the east-west direction in any other direction. It will always stay in north-south direction. This property of magnet, or what it was known as magnetite, was discovered by Chinese people. That is why magnetite is also called a lodestone. This magnet is also known as a lodestone because lodestone means leading stone, which leads us in towards north-south direction. Because it always aligns itself in north-south direction, it always leads towards north-south direction. That is why it is also known as a lodestone. The natural magnets have irregular shape. They do not have any irregular shape and are weak. And are weak. Their magnetism is weak. When a piece of iron or steel is rubbed with a natural magnet for some time, it acquires the property of magnetite. That is magnet. It acquires the property of magnet, or what we call it acquires the property, magnetic property. Such magnets are called artificial magnets. Artificial magnets have desired shape. We can make it of any shape, make them of any shape, and they have desired strength, and we can make them of any strength. They are stronger than the natural magnets. A bar magnet which you see in your laboratory or in your homes or around you, they are all artificial magnets. Horseshoe magnet is also artificial magnet. It is rubbed with a natural magnet, and magnetic needle or compass needle, etc. All are artificial magnets. Now, what are basic properties of a magnet? The first property of magnet is that is attractive property. A magnet can attract small pieces of magnetic substances like iron, steel, magnetic substances which are attracted by a magnet are known as magnetic substances. Wood is not a magnetic substance, so it cannot attract wood, grass, etc. or plastic. They are not magnetic substances. It always attracts only magnetic substances. This is known as the attractive property of a magnet. So what you have to remember is that the first property which a magnet possesses is an attractive property. The attraction is maximum at poles. If you have a pile of nails and you put a magnet in it, when you bring out the magnet from the pile of nails, you will see that most of the nails are attracted at the ends. That is why we say that the attraction is maximum at poles, at North Pole and South Pole. The poles are situated a little towards inwards from their geometrical ends. For you must remember this thing. The poles are situated a little inwards from the ends of a magnet. The length between the north and south pole of a magnet is roughly 1 by 6 of the length between the two ends of the magnet. For example, if we have a magnet of total length 6 meters, and when we multiply 6 meters by 1 by 6 we get 1 meter. So we have to go inside half a meter from both the ends, half meter from one end to reach the north pole, and half meter from the other end to reach the south pole, half meter inwards the end of the uh, magnet. Then there is another property that is known as derivative property. What derivative property means is a magnet when suspended freely always aligns itself in the north-south direction. It will always remain in the north-south direction. This is the second property that is known as derivative property of the magnet. The pole which points towards geographical south is called south pole, and the pole which points towards geographical north is called the north pole of the magnet, because Earth has its own magnetism. It has its own poles, north pole and south pole. So the geographical south pole, we have Earth's magnetic north pole, and towards the geographical north pole we have Earth's magnetic south pole. So south pole will attract the north pole of the bar magnet when it is suspended freely, and the north pole of the Earth's magnetism will attract to the south pole of the bar magnet. So bar magnet's north pole will always be towards the north pole of geographical north pole, and its south pole will always be towards the geographical south pole. Then there is third property: like poles repel each other, and unlike poles attract each other. The North Pole and North Pole will repel each other. The South Pole of one magnet will repel the South Pole of the other magnet. But the North Pole of one magnet will always attract the South Pole of the other magnet. The force of attraction or repulsion between the two poles of set angle M1 and M2, separated by a distance R, is given by Fm is proportional to M1 M2 by R square, or Fm is equal to K M1 M2 by R square. This implies F1 is equal to mu naught upon 4 pi M1 M2 by R square. This is called Coulomb's law of magnetic force, or Coulomb's law of magnetism. We have also Coulomb's law in electrostatics. F E is equal to K Q1 Q2 upon R square. Similarly, here we have F M is equal to K M1 M2 upon R square. Magnetic poles exist in pairs. A single magnetic pole does not exist. It is a correction. A single magnetic pole does not here it is exist. it is exist here. A single magnet pole does not exist. If you want to break a bar magnet into two pieces, you will still the two pieces will have their own north and south poles. There will not be a single pole. South pole will cannot be separated from a north pole. North pole cannot be separated from a south pole. Magnet is cut into two equal parts, transverse to its length, and south pole of the magnet do not get separated. It is actually there is again a correction. Mm, South pole and magnet pole cannot be separated. Each of the two parts of the magnet have north and south pole at two ends. Each part has the same magnetic strength as that of the original magnet. So if you cut the magnet into 4, 5, 10 parts, every part will have its own north and south pole, and the strength of every north pole will be equal to the strength of the original magnet. Now there is inductive property. When a piece of magnetic substance is brought close to a bar magnet, for example, when iron is brought close to a bar magnet, it occurs magnetism. It becomes a magnet. The magnetism occurred is called induced magnetism. If you bring a nail close to a magnet, the nail itself will become a magnet. So, though it will last for some time, but it becomes a magnet. Magnetism is induced in it. That is called the inductive property of magnet. Then there is another property. Repulsion is the surest test for distinguishing between a magnet and a piece of iron. If uh, a piece of iron is repelled, then we are sure that iron is also a magnet. If it is not repelled, if it is attracted, then we are sure that it can be a magnet or it cannot be a magnet. If anything, it is not necessary that iron, if you have any substance and you bring a magnet close to it, if it attracts it, you must not be sure that the piece which was attracted by the magnet is surely a magnet. It can be or it cannot be, but if it is repelled, it is surely a magnet. Now, what is magnetic field? Like electric field, here we will have a magnetic field as we have this gravitational field, nuclear field, electric field, and magnetic field. The field around a charged body is called electric field. Similarly, the field around a magnet is called magnetic field. The space around a bar magnet or wire carrying current, because a wire carrying current will also produce a magnetic field around it. So up to which its effect can be felt is called a magnetic field. It is denoted by B as electric field is denoted by E. Remember that magnetic field is not denoted by M, it is denoted by B. Remember this thing. Magnetic field is denoted by B. And the SI unit of magnetic field B is Tesla. As the SI unit of electric field is Newton per coulomb. Here the SI unit of magnetic field B is Tesla. Now this magnetic field, like electric field, it can be uniform, it can be non-uniform. So what is uniform magnetic field? The magnetic field in a region is said to be uniform if the magnetic field vector B has the same magnitude and same direction at all the points in the region. Suppose if there is a magnetic field in our room, and if we choose any point in our room, then the magnitude of the magnetic field at that point must be same, and the direction of the magnetic field must also be same. So if the magnetic field has same magnitude and same direction at all the points in a region, then the magnetic field in that region is said to be uniform. A uniform magnetic field acting in the plane of the paper. For example, if you have a paper and if the magnetic field is parallel to the plane of the paper, it is represented by parallel lines equidistant from each other, as you can see from the figure. These arrows, they are of equal length. Number one, they are equidistant from each other. So if you see this thing, then the magnetic field, this shows that the magnetic field in the region is uniform. and it is acting parallel to the plane of the paper. Now, if the magnetic field is perpendicular to the plane, for example, if you are sitting in a room on a carpet and you put your pencils on the carpet and you keep them equidistant from each other and all the pencils are of equal length, then the pencils will represent a uniform magnetic field parallel to the plane of the paper. Now, if you put the pencils at right angles to the surface of the carpet, what will happen? Then the magnetic field is denoted by dots. The dots are equidistant from each other. These dots show that the magnetic field is uniform because the dots are equidistant from each other and the magnetic field is perpendicular to the plane of the paper directed inwards from upper side to lower side. So then we have to if the magnetic field is if the magnetic field is perpendicular to the plane of the paper and directed upwards, as you can see from this figure, then it is represented by crossed lines and they are also equidistant from each other. These crossed lines show us that the magnetic field is perpendicular to the plane of the paper and it is directed upwards. If the dots are there, they are perpendicular to the plane of the paper but directed inwards. Now, if there is a non-uniform magnetic field, non-uniform magnetic field can be represented uh, by divergent or convergent lines, as you can see from the figure. This figure show us that the magnetic field is non-uniform and it is moving outwards. And then there is another figure on the right side of this paper page. You can see the magnetic field is convergent. The magnetic lines are convergent, so this shows that the magnetic field is non-uniform. Now, magnetic lines of force. Magnetic lines of force. So what is a magnetic line of force? The path along which the magnetic needle, compass needle, aligns itself in a magnetic field is called a magnetic line of force or a magnetic field line. You have to bring a magnetic needle and the direction along which the magnetic needle or the compass needle aligns itself will show us the magnetic line of force. If you want to draw a magnetic line of force as you might have done it in your class 10th, you have to put the magnet, bar magnet on the plane of the paper and then bring a compass needle close to it and move it from north pole to south pole. You will see the lines as shown in this figure will be formed like this. So, what are the properties? What is the magnetic line of force? A path along which the magnetic needle or compass needle aligns itself in a magnetic field. So, these are all magnetic lines of force. So, what are their properties? Let us discuss them by one. So, here you can just see two, but it has many properties like electric lines of force. They are almost similar. Almost similar. The properties which we have discussed while discussing electric lines of force or electric field lines, they are the same, but there will be a little bit of difference. I will tell you that. First property is the magnetic lines of force are hypothetical and do not exist exactly. As in case of electric lines of force, they are also hypothetical and they do not exist actually. Now the second one is magnetic line of force are continuous closed curves. This is the difference. This is the main difference between electric line of force and magnetic line of force. In electric line of force, they are not continuous. They are they originate from positive charge and terminate on the negative charge. They start from somewhere and terminate at somewhere. But here, the magnetic lines of force are continuous. They do not originate from anywhere or terminate from anywhere. But outside the bar magnet, the direction of the magnetic line of force is from north to south. Remember this, as you can see from the figure. Outside the bar magnet, the direction of magnetic line of force is from north to south, and inside the bar magnet, they pass through the body of the magnet. Though I have not shown it here, but they pass through the, as you can I can show you here. Well, this inside the body, this is the magnetic line of force. Then there will be another line that will be parallel to, like this. So inside the bar magnet, the direction is from south to north, but outside the bar magnet, the direction is from north to south. Then another property is that no two magnetic lines of force intersect each other, ever intersect each other. As in case of electric lines of force, they also do not intersect each other. Similarly, magnetic lines of force do not intersect each other. So this the density of the magnetic line of force gives us the magnitude of the magnetic field. As you can see here, the in this region, the magnetic lines of force are very dense as compared to this region. So here in the first case, the magnetic field will be strong, and in the second case, there is a much space between the magnetic line of force. They are not dense, so the magnetic field will not be as much strong as it will be there. Similarly, uh, the tangent, if we draw a tangent to the magnetic line of force at anywhere, as I can show you here, when I draw a tangent here, this is a tangent. This will give you the direction of the magnetic field at that point. If we draw a tangent to the magnetic line of force at any point, that gives us the direction of the magnetic field at that point. So here, the magnetic field will be in this direction. So that is enough for today. Inshallah, see you tomorrow. Thank you.